Welcome to Module 5, Part 0. We'll go over gas mixture. Specifically, we'll use perfect gas mixture model. We'll introduce a new model, a PG mixture model, to describe a gas mixture. And we'll solve a problem, simple problem, with verification, of course. The prereq for this section is Module 1, Part 2, where we discussed the original PG model covered in Chapter 3 of your textbook. This is in Chapter 11, the last part of Chapter 11, where gas mixtures are defined. So we'll begin with very basics. What we understand by mass versus mole, the two way of describing the amount of a system. So we go way back to Chapter 1 with an animation there. This is a screen capture from a slide from Chapter 1. And it describes basically how do we define or express the amount of matter in a system. Well, the first way obviously is mass. We will understand that mass is expressed by the symbol m, and the unit used is kg. So the amount of matter in a system is simply its mass, so many kilograms. The second way of expressing how much matter is there is to count the molecules. Again, here we are talking about a pure substance, and by the way, a pure substance means if you scoop a little bit of material from here versus there, you'll have the same composition. So air in your room right now is a pure substance, because if you scoop out some air from one corner versus another corner, you'll have the same amount of oxygen and nitrogen in it. In other words, the composition doesn't change with space. And thermodynamics, mostly all the laws we have been covering, deals with a pure substance, because they're valid for pure substance. And if you have a more complex system, say a piece of copper in water, then we divide that into two different subsystems. Well, now we'll simplify the system even further, and let's say we have not only have a pure substance, but we have just a single molecule everywhere. So let's say this system is made of a pure oxygen or pure nitrogen or pure carbon dioxide, etc. In that case, the mass is expressed again by mass m, and the number of molecules in the system can be expressed by what is known as mole, expressed by symbol n, and the unit becomes kilomole. And this is a little bit of confusion here, because look at the spelling, mol versus mole. Mole is the quantity, is the property, such as mass. What is kilomole? Is essentially a count of, it's like a big dozen, and is equal to a very big number. You probably remember this number as 6.023 × 10^23 from your chemistry class, but notice that we are talking about kilomole, which means 1,000 mole. So that's why the number is so huge. So it's important to understand here, not to memorize the number. That number is not so important, but a kilomole means a huge, huge, huge number of molecules. So first thing first, so any given system, we can express how much matter is there, so many kilograms or so many kilomole. And as we understand from chemistry, that each molecule must be identical. What is a molecule after all? It is the smallest unit of a material. If you take water and keep breaking it into smaller and smaller pieces, the smallest piece of water that you can find is the water molecule. If you break water any further, it will become hydrogen and oxygen, which are totally different from H2O. Likewise, when we say oxygen, we mean oxygen molecule, not oxygen atom, because that's the smallest unit of oxygen gas. We breathe oxygen, we cannot live without oxygen. But if you break the oxygen molecule, it will become oxygen atoms. And oxygen atoms are very corrosive. In fact, it will kill us in no time. Whereas O2, oxygen makes us live, oh, the oxygen atom will kill us. So in chemistry, when they say oxygen, sometimes they mean oxygen atom. But in engineering, whenever we say oxygen, nitrogen, carbon dioxide, we mean molecules. We mean a system made of a pure substance, and that is the smallest component, smallest unit of that substance. That's the molecule. So therefore, since each molecule is identical, we can define a constant, mass per kilomole. In other words, it must be a fundamental constant. It's mass of so many molecules. Suppose we have identical apples in a big basket, and if somebody says, what is the mass per dozen apple? Of course, that will be a constant if all the apples are identical. It doesn't matter which dozen apple you pick up, the mass will be so many kilograms, so many pounds. So that's an apple constant, we can say. Similarly, an oxygen constant will be what? The mass of so many oxygen molecules. And that's called the molar mass. We'll put a bar on top. The molar mass of a substance is a constant, of a pure substance is a constant. It is the mass per unit mole. So it's mass per unit mole is the molar mass. Molar mass of several substances are listed here, but it's good to memorize a few. For instance, molar mass of oxygen is 32 kg per kilomole. Notice that we'll always add unit to molar mass, whereas in chemistry sometimes they skip the unit because they just compare the mass of a molecule with that of hydrogen atom. For engineers, it's very important that we understand what the unit means. So molar mass of nitrogen, for instance, is 28 kg per kilomole, which means if you take the same number of nitrogen, a kilomole of nitrogen, you will get 28 kg. A big dozen, or a kilomole of oxygen will have a mass of 32 kg. So for a pure substance, for a pure gas, it's clear what the molar mass means, and we can easily extend that definition to a mixture. So if I have a mixture which may have different kind of molecules in it, the total mass will not say M total, we'll just call it by M, and a given component we might describe it as Mk. So if I sum over all the masses, M1 plus M2 plus M3, so we are summing over K, but we'll pretty much drop that subscript. We'll simply write it as summation of Mk for quick expression. So it should be understood immediately. The total mass is sum of all its components. So if I have a box with different gases, say oxygen, nitrogen, carbon dioxide, and I know mass of each component, all I have to do is to add those masses. Sometimes they're called partial masses to get the total mass. Similarly, if I want to know what is the total number of mole, what is the total mole in the gas or in the mixture? What is mole? Mole is essentially the count of molecules, right? So if I know how many oxygen, how many nitrogen, etc. are there, so all we have to do is to add the number of each components. So we can write a similar equation. Obviously, the unit of N would be kilomole, and unit of mass will be obviously kilogram. Therefore, we can define the molar mass of a mixture. What does that mean? It's kind of like an average molar mass. It is the mass divided by kilomole. So this becomes a universal formula for us, that molar mass is M by N. So you can just turn it around and convert, say, mass to mole or mole to mass. So suppose in a mixture, we know the mass of, if we know the mass, we can go back and forth. So we can write the different formulas like this. And this is true for a mixture, and this is true for a component. For a component, we are simply going to add the subscript Mk, as you can see, And you can quickly see that it totally makes sense. So in other words, when I have a mixture, I can look at it as if it's a sum of different components. It has so many mk amount of partial mass of each component and nk amount of partial mole of each component, resulting in a molar mass, a mixture molar mass of this. Okay, let's now introduce a couple of more properties of a mixture. So if you have an mkg of a mixture and each component has a mass of mk kg, mk is sometimes known as the partial mass of component k. And that brings us to a definition of the mass fraction xk, which is the partial mass over total mass. And you can think of it as a fraction having no unit, or you can call it kg of k by kg of mixture, because really the two kgs are not the same on top and bottom. So xk is called the mass fraction. So when we have an mk kg of a mixture, each component has a mass of mk kg. The physical meaning of xk could be, suppose we start with 1 kg of a mixture, then it will have xk kg of k in it. So that's another way of looking at it. And if we sum over all the k's of the mass fraction, we know all the fraction add up to unity, but we can prove it very easily by definition. This is what? M is a constant, so it comes out of the summation, just like as in an integral. Or if you want to expand and show the same thing, we can write it like this. Sum over all components. M is the total mass. So what we get is M1 plus M2 plus M3 at the top, which is M over M equals 1. So this is an important relationship, that summation of xk is 1, because if the mass fraction of many different species are given, the last species, its mass fraction can be obtained by summing all the species mass fraction to 1. In a similar way, the molar description of a mixture can be converted into mole fraction. Again, suppose we have a mixture n kilomole with nk kilomole of k in it, n1, n2, n3, etc. Then, of course, n is summation of nk by definition. And we can define the mole fraction yk as nk over n. And just like we did for mass fraction, we can show that summation of yk is also 1. And a mixture can be expressed in terms of 1 kilomole with yk kilomole of component k. Again, the mole fraction also, you can think of having a unit of kilomole of k per kilomole of mixture. Now that we can express a mixture in terms of its mass fractions or mole fractions, let's find a way in which we can go from mass to mole fractions or mole fraction to mass fraction. So let's begin with a mixture where the mole fractions are given. Suppose yk of a mixture is given. In other words, a mixture is composed of so many, the oxygen mole fraction of this, nitrogen mole fraction of that, etc. How can you find, the question to us is find the molar mass of the mixture and also find xk of individual species. So we start with 1 kilomole of the mixture, and we recognize that it is yk kilomole of k in it. So the partial mass of component k in this mixture, mk, is given by yk times molar mass of k. So in this 1 kilomole of mixture, we have yk so many kilomole of k times molar mass as a unit of kg of k per kilomole of k, and that's how we get kg of component k, mk. So the total mass of the mixture becomes summation of mk is summation of yk mk bar so many kg. So now that we know the mass of 1 kilomole of the mixture, how much is our n? Is 1 kilomole. So therefore molar mass must be m over n, which is simply yk m bar k divided by 1, which is so many kg per kilomole. So we have a very simple way to find the molar mass of a mixture is simply the mole fraction weighted molar masses of components. Now to finish up, how do you find the mass fraction of a component? The mass fraction is the partial mass over total mass. mk, we already have an expression for mk divided by m. For m we have summation of yk mk bar, or if we substitute the expression for m bar from the above equation, we can write this simply as mk bar over m bar. Now we can go and find solve the reverse problem of calculating yk from given xk's. Now let's do just the reverse of this. Suppose a mixture is given, and the mixed in terms of mass fraction, then we begin with 1 kg of the mixture. If we start with 1 kg of the mixture, and our goal is again to find m bar, the molar mass of the mixture, and mole fractions. Again, in the future modules, you will see the importance of that, finding yk and xk from each other. And our derivation is we'll take the familiar path. Now that we know the mass of individual component, let's find out what is nk, because we know the mass of the component in that 1 kg of the mixture. So mass by mole is simply sk so many kg of k per kg of mixture, right? That's the definition of xk, and molar mass has the unit of kg of k, molar mass of k per kilomole So therefore, this get cancelled, kg of k, so we get kilomole of k per, just 1 second. Okay, now suppose we have a mixture where the mass fractions are known, and we are to find molar mass of the mixture and components, the mole fraction of each component. So we'll start with 1 kg of mixture, and it will have xk kg of component k. So therefore, what we can write is that the the number of moles, the mole of the component K is given by the mass of the component K divided by the molar mass. We have so many kg of K, and molar mass is kg of K per kilomole of K, right? So we get Nk is the kilomole of K, so many kilomoles in that mixture of 1 kg. So what is the total mole we have? Total mole we have is summation of that, which is summation of xk over m bar k. You understand that is if I have x1 kg of component 1, x2 kg of component 2, this is how the summation goes. So what is the total mass of the mixture? Of course, we started with 1 kg, we still have 1 kg. So therefore we can get an expression for molar mass, which is mass over mole. How much mass we have? 1. And how much mole we have? Summation of xk over m bar k. So many kg per kilomole. And the expression for yk, which is mole of K by total mole. Mole of K, we have an expression xk over m bar k divided by n, summation of xk over m bar k. And notice that 1 over this is molar mass. Therefore, we can write it as molar mass of the mixture. So we have a simplified looking formula. So if I know xk for each component, therefore we can figure out for a mixture where xk is given, how to find yk. Notice that xk, which is a mass fraction, in one way we can say it's a fraction, it doesn't have a unit, but what xk really means is kg of K per kg of mixture. So if kg, you can say it's unitless, but also you can put a unit if you want. And if I have 1 kg of mixture, that's why it has 1 kg of xk kg of K. So the unit of xk, sometime it can be expressed with a unit, or sometime it's left unitless, because really there is kg and kg get cancels out. But if you look at the real meaning, xk means so many kg of K, and denominator is kg of the mixture. So sometimes this is the unit that is used. That's why we have here xk kg of K, and we divide, and that's from where we are finding yk, which is kilomole of K per kilomole of mixture, the mole fraction. Okay, now let's do a quick example. Suppose we have a mixture is given that X of oxygen is 0.23 and the rest is nitrogen. So obviously nitrogen will be 1 minus 0.23. And let's say this is how we're going to model air. So we have 1 kg of air. And the question is, find m bar and y oxygen, y nitrogen. Essentially is a repeat of what we have done in the last. We could use in the last slide, and we could just use the formulas to calculate our answers, but we can also go from scratch. How we do that? Because the mole fractions are given, we can find how much oxygen is in there is X of oxygen by molar mass of oxygen, which is 0.23 over molar mass of oxygen is 32. So many kilomole of oxygen. And nitrogen we can similarly find from 0.77 divided by the molar mass of nitrogen, which is 28. So therefore, we can find the total mass as, the total mole as, so the total mole becomes, you can calculate that to be 0.03468 kilomole, and the oxygen amount, by the way, was 0.00718, and the nitrogen amount was 0.0275 kilomole. So now that we know the kilomoles of nitrogen, oxygen, and the total kilomole, and the mass is of course 1 kg, so therefore molar mass of air becomes m by n. Mass is 1, 0.03468. That turns out to be about 28.84. And generally, this is approximated as 29 kg per kilomole for air. That's a standard. The reason is that it is not just rounding up. It is because air has a tiny bit of CO2, and CO2 is heavier than nitrogen and oxygen with a molar mass of 44 kg per kilomole. So that has a tendency to raise this. So this is a very good approximation that air has a molar mass of 29 kg per kilomole. So if you want to find the amount of air in your room, just find the volume, and you can use, PV equals MRT to figure out exactly how much mass you have. PV equals, nRT. We'll come back to this formula a little later, but let's finish the problem at hand. To find the mole fraction of oxygen, and oxygen by total mole, we have already calculated both of them, 0.0718, and total mole was 0.03468, and that gives us a mass mole fraction of 0.207, which is approximated to be 0.21. So it's a common knowledge that oxygen, the mole fraction of oxygen is 0.21, whereas the mass fraction is 0.23. This is an important number to remember. Of course, Y of nitrogen is simply 1 minus that. So Y of nitrogen will be 1 minus 0.21, which is 0.79.